Okay, good morning. Good morning, everybody. Well, today we have a seminarist here, Iacopo Bartalucci, who is visiting us. Well, he's on holiday here in Tenerife, but he kindly visited us for doing this seminar today on galaxy clusters, mainly focused in the X-rays. On X-rays data, no, from the X-rays, analyzed from the X-rays point of view. Iacopo did his PhD thesis in Rome, and now is working as postdoc in Saclay, a group with we are collaborating, the group of led by Monique Arnaud. And well, I think this is a good opportunity for us, researchers, the few people here in the EIC, that we develop our research on galaxy clusters. So, Iacopo, when you want.
Sorry. Okay, so as I was saying, this work is actually part of a much bigger project, which is the M2C project led by Monique Arnaud, with all the colleagues that I've listed here. This is an ERC funded project. Okay, so here is the outline of my talk. I will start by briefly introducing galaxy cluster and why galaxy cluster are so interesting for us. Then I will talk about the sample that we used for this M2C project and for our work on this 5 galaxy cluster, and the observational challenges that we had to face to characterize this galaxy cluster, and how we overcome these challenges by using Chandra and XMM-Newton, and in particular by combining the 2 telescopes. Then I will portray individual profiles and the individual properties of this galaxy cluster, and then I will draw my conclusion and talk about some future prospects. Okay, so let's start with some brief recall of cosmology. So we know that according to the cosmological model, the structure on large scale that we see today, which are traced by the distribution of galaxies that we see here in this infrared map, are originated from the tiny fluctuation in the primordial density field that we see here in the CMB. So, if we are able to study the evolution of this structure, which means basically how these things ended up like this, we are able also to do cosmology, because we know that the evolution of large-scale structure is tightly linked to the properties of the universe itself. Now, how can we characterize the evolution? Now, from simulation, and in particular, as we can see here from the simulation of Lebrun et 2018, we start from a condition where the dark matter, where we see small fluctuation here in the dark matter distribution at very high redshift, and then as we go, as time goes by, we end up with this sort of cosmic web structure, where at the intersection we find galaxy clusters. So galaxy clusters evolve and form at the nodes at the intersection of this cosmic web. So galaxy are excellent tracers of how large structure assembly and evolve. So that's why we are so interested in galaxy cluster. And just to give you an idea of how sensitive galaxy clusters are to cosmology, here I show the results from Vikinin et al. 2009, where they are plotting the distribution of galaxy cluster at a certain mass as a function of redshift. And you can clearly see here the points measured and the fit here with these solid lines. And you see that if you slightly change the values, for example, of the dark energy content, omega lambda, you see that fit dramatically changes. So this plot shows nicely how sensitive galaxy clusters are to cosmology. Now, as I've shown, if you want to do cosmology with galaxy cluster, we have to measure the mass of a galaxy cluster. What is the the content of a typical galaxy cluster. Now, despite their name, the main matter galaxy cluster is dark matter, which forms basically more or less 85% of the total matter component. Then the main baryonic component, which is formed by a hot called the ICM, which fills the intracluster volume. And you can see this component here with this purple cloud here, that basically fills the cluster volume. And then only a very tiny fraction of the baryon mass is formed by galaxies and stars. So, of course, we cannot directly measure dark matter. Interesting thing that we can use these baryonic components to trace the dark matter component. Now, another interesting properties of galaxy cluster is the fact that if we assume that galaxy cluster evolution is only driven by gravity, we are in a self-similar evolution scenario, which means that if we take, for example, the dark matter radial profile that we see here, or the gas profile that we see here, they should be circular, independently from the mass of the galaxy, once we rescale them. And for example, this is a prediction that with the famous Navarro-Franken-White profile or the Einasto profile. Now, this profile is interesting because, for example, we know their evolution depends also on the cosmology, because, for example, the slope of these profiles at the center depends on the density of the stars at the time of the formation of the galaxy cluster. So, by studying the evolution of these profiles, we can do cosmology. And also, we see some dispersion for these profiles. And this dispersion is related to the detailed individual history of formation and assembly. So, if we want to do cosmology with galaxy cluster, we can measure the mass, or we can look at this, now, everything I said for this seminar scenario is valid for objects which are realized and non-gravitational processes are negligible. Okay? Now, what happens actually in the reality with galaxy cluster? That the assembly and evolution history of galaxy cluster is characterized by a plethora of physical processes. For example, here in the left, you see a very famous galaxy cluster, which is the bullet cluster. And what you see here is the X-ray emission here, and where here you see the yellow, this is the core of the cluster. And what you're seeing here is basically you have a main halo, which is this one, and then you have a smaller halo, which is basically merging and passing through the main halo, forming this sort of like a bubble. And so you have all the gravitational processes related to that. For example, you have shocks, you have core fronts, you have the fact that the bulk of the dark matter is moving because of this smaller halo that is passing. And another interesting feature, for example, here is that you see that the X-ray emission is not tracing the actual dark matter component, which is shown here with lensing isocontours. And also another thing that we have with galaxy clusters that we non-gravitational processes. For example, here, if you look at the core, the Perseus cluster, which is a very nearby galaxy cluster in X-ray, you see that inflating the gas and creating these bubbles which are rising up these are actually galaxies which is being disrupted by the activity of the eccentric GN. So, often, if you read the paper, you see that galaxy clusters are referred as cosmological probes. But I will to say that in order to use galaxy cluster as cosmological probes, you also need to understand the physics which is behind the formation of galaxy cluster. So I prefer to say that galaxy cluster are actually crossroads between cosmology and astrophysics. Okay, so how do we characterize galaxy cluster? Okay, we have seen that galaxy cluster are formed by so we can look at different wavelengths. The first one is looking at the optical, so we are at galaxies. The good thing, the optical to characterize as galaxy cluster, to detect the galaxy cluster in optical, because we have large large portion of sky covered by surveys, for example, SDSS or other surveys. we have is that galaxies at high redshift are faint, so it's hard to get at high redshift using optical. Optical is also very good for mass determination because we can use some techniques to directly relate some observables of the galaxies with the dark matter potential. For example, we can use lensing, or we can use velocity dispersion by correlating the velocity of the galaxies with the total with the potential well of the dark matter. And then we could also use some proxies. For example, we can use the richness to simply count the galaxies and get the mass of the cluster. Then optical is also good for physics because, for example, in optical it's easy to find substructure and clumps which are falling and are interacting with the main galaxy. We can study the evolution of galaxies. So galaxy clusters act as laboratories to study the evolution of galaxies with the environment. The only problem that I see is that it's a bit hard to directly relate the impact of the evolution of galaxy cluster with galaxy observables. There is not connection between these two. Then there is the X-ray ICM, which is an emission via a thermal Bremsstrahlung. And in particular, as you can see here, in the X-ray, we are able, the emission is proportional to the density of the gas and to the temperature here. So in X-ray, we are able to density temperature of the gas. Now, for X-ray, it's quite nice to detect galaxy cluster because it's easy to validate a galaxy cluster. If we see an extragalactic emission which is diffuse in X-ray, it's likely that galaxy cluster. There are, however, some problems. The first one is that they are faint at high redshift because they suffer from cosmological dimming, and also the sky is not so good as in the optical because, for example, we have a RAS, but the is that RAS and also the PSF is not so good. Then the X-ray is very good determination. You can assume that there is the hydrostatic equilibrium between the gas, the dark matter potential, and so we can infer the mass of the cluster, and we can also use some proxies. For example, here we can use X, which is a proxy measures, if you want, the pressure of the gas, which is somehow related to the total content of the cluster. And then X-ray is really the best to do physics because it's easy to find substructure and we can directly see the impact of the evolution history of galaxy cluster gas. Because as I said, in X-ray we can directly measure the density and the temperature, and we can directly see all the physical processes which are happening in the ICM related to the evolution history. And also we can directly get a lot of information on thermodynamic properties, for example, temperature, density, pressure, entropy, and so on. And then another very useful value is the microwave through the Sunyaev-Zel'dovich effect. Now, the Sunyaev-Zel'dovich effect is an effect for which you have that the CMB photons are scattered to higher energy, interacting the what you are actually looking at when you're doing the SZ is actually you are looking at a distortion of the CMB spectrum. And here you see the same cluster that but SZ is really the best for detection because, first of all, galaxy clusters, when you're looking at galaxy clusters, they are somehow retroilluminated by the CMB. So you do not suffer from cosmological dimming. That's also another good with SZ is that multiple deep and large scale surveys, for example, Planck, SPT, ACT, and so on. SZ is quite nice for mass using, and SZ is also very good for physics because basically you are probing the same medium as the X-ray because, as I said, the SZ is the interaction of the ICM with the CMB, so you are looking at again at the ICM. But the problem is that SZ you are measuring. You need X-ray to get access to all the other thermodynamic. The picture that is emerging from everything that I said so far is that basically if you want to if you want to use galaxy cluster as cosmological probes, you need to study the evolution of the dark matter and of components, looking at files, and also you need to study the physics of galaxy cluster, and that is exactly the content of the project. And as you can see, the is complete use of hot and cold baryons and evolution. So we are doing cosmology and identify the thermodynamic state of this galaxy cluster up to redshift 1. So to do astrophysics. Now, to do all these things, basically the working groups that are related to this project. So first of all, we have to find the cluster using X-ray and SZ, and this group is led by Paola Tarrio and Jean-Baptiste Melon. Then validation of galaxy clusters, so we have a list of candidates, and then we do the validation, and this group is by Remco Vanderburg, Stefano Zaratini, and Hervé Ossel. And then there is the characterization of galaxy clusters, so we do physics and cosmology, using X-rays and optical, and that's the part where I'm working in with Monique Arnaud and Gabriel Pratt. And then we are continuously comparing our results with a suite of cosmology that have been produced to exactly match the cluster that we are looking at. And this group is led by Amandine Lebrun and Romain Tessier. Okay. First of all, the first part of this project is to get a sample. The first thing that we had to do is to build the sample that we used to do this project. Now, the sample for the M2C builds on SZ large-scale surveys, and in particular Planck and SPT. So we're using the because first of all, as I said before, we want to look at the evolution of dark matter and baryonic profiles to a very high redshift if we want to do the evolution. Now, we know that for redshift below 0.5, we have a quite good literature on that. So we have to push our analysis towards higher redshift. And in particular, redshift 1 to redshift 0.5. So, as I said before, the SZ is really the best tool to go at higher red. And the SZ is very good because what we are measuring with SZ, as I said before, is the pressure. And the pressure somehow by the theorem at very first order is related to the total energy content of the galaxy cluster. So an SZ selected sample should be an unbiased mass selected sample. So we are basically selecting to, but be aware that we are still suffering from the Eddington bias. And then our project is focusing at looking at very massive galaxy cluster. Why massive galaxy cluster? Because if we take very massive objects, we are somehow saying that we are in a regime where we can neglect non-gravitational physics, only gravitational physics. The problem with very massive cluster is that they are intrinsically rare. So we have to use to look at the SZ to find a lot of these objects. Okay, so here you can actually the sample that we use in this work. So in the redshift mass plane, you see all galaxy cluster which have been detected by Planck, SPT, and ACT. And the gray area here identifies the region we are interested in. In particular, all galaxy cluster from redshift 0.5 redshift 0.1 and with a mass of 10 to the 14 solar masses. So we divided the sample in 3 beams because we are using different techniques for each beam, and my work focused on the beam 3. So my work is focused on the X-ray 5 very high redshift and high mass galaxies that you can see here, where we have 5 objects. Now, since we want to do, we want to study the physics of these objects, we have to have a deep X-ray and excellent coverage, and that's the case. We have both Chandra coverage and XMM-Newton coverage because we have for example, we have the SPT follow-up, observation of individual objects, Also, we have some XMM-Newton deep coverage led by Monique Carnot, and also validation program. So you see that we selected this object with straight coverage. Now, I talked about Chandra and XMM, but maybe it's worthwhile to give some very information. So Chandra and XMM-Newton are X-ray satellites which basically operate band from 0.3 to 10 kV. Now, the most important features that I would like to talk about today is the fact that Chandra has a very good angular resolution, while XMM has a worse angular resolution but a very large effective area. So I would like to say that for our purposes, Chandra and XMM are actually complementary instruments. And to show you that, here you see two galaxies, Chandra on the left and XMM-Newton on the right. So you see, for example, that this cluster 717, you see that with Chandra you can resolve some interesting feature here in the core, and you can actually see all these point sources, which are AGN, which are emitting in XMM. While on the right with XMM-Newton, because of the poor PSF, you basically lose all this kind of information. But here, for example, this other cluster with Chandra, here you see that at 0.8 arc-minute, the Chandra isocontours start to become noisy. While with XMM-Newton, because of the bigger effective area, and so because of the large statistic, you can still detect good signal up to 2 or even 3 arc. So, sorry. What is the? It's a logarithmic spacing of. It's logarithmic spacing of square root of 2. Log 2. Okay. The complement is even more critical when we are looking at high redshift objects, as in the case for the sample that I used in our work. You see a Chandra observation of a galaxy cluster at redshift 1 and a Chandra observation of a galaxy cluster at redshift 26. So you can clearly see the dramatic influx of the cluster dependent shift. They have a similar mass, so they should be more or less. They should have more or less the same luminosity. And in order to overcome this problem of the cosmological dimming, to XMM-Newton because it's a bigger effective area. So you can clearly see that in this XMM-Newton observation of the same galaxy cluster that I'm showing here, you are able to retrieve the flux that you lost because of the cosmological dimming. But you still have the problem of the AGN confusion. For example, here you see that the point sources that you see with Chandra, so the AGNs, that you actually see as point sources, in XMM-Newton you see them as very large sources, which have angular sides more or less similar to the object that we are looking at. Now, since we want to combine these two instruments, because we want to have both a very high resolution and large statistics, ask ourselves, are we able to combine Chandra and XMM-Newton to observe high redshift galaxy clusters? Now, the answer from several papers, if you look in the literature, is can combine Chandra and XMM-Newton for density profile because it's a flux rate and you have small differences of the order of few percent, and not can't for temperature profile because there is a bias of 10-15% between the two instruments. Now, since we are looking at a very high redshift, cluster, we actually kind of extended the question and we asked ourselves, are we able to combine Chandra and XMM density profile and temperature profile? And the question arises from the fact that, for example, here you see an XMM-Newton observation of a very nearby galaxy cluster and of a galaxy cluster at redshift 1.13. And you can clearly see that from an instrumental point of view, these two objects are very different. So, the first thing is, are we able to combine temperature profile? So, we, as said before, in the literature, you can find that the answer is generally no, we can't. But what is the problem related to the temperature difference between Chandra and XMM? Now, in X-ray, what X-ray astronomers do, measure the temperature, is actually fitting the continuum of the spectrum. So you extract the spectrum from a region, fit the continuum. And for example, here you see the corresponding continuum here. The problem is that when you are fitting the continuum, you are very sensitive to the effective area, and so you are very sensitive to the calibration of the instruments. So very small differences in the calibration of the instruments give birth to very high differences in the temperature. But the nice thing is that we are looking at very high redshift objects. So what happens is that the effective temperature is actually shifted because of the redshift to the effective temperature that we are measuring is actually shifted to very low energies. So for example, a cluster of 5 kV is shifted to lower energy. And as you can see in some So we don't actually have this problem of the temperature calibration between Chandra and XMM with high redshift objects, because effective temperature lower energy. And what happens for density profiles? Now, we actually dedicated a paper to that, and the answer, so this is a very technical paper, but the only interesting thing is that even if we are dealing with very expensive redshift, we can say that density profiles can still be combined. Comparison between Chandra and XMM set of common cluster, and you see that all the points basically lie on the identity line. And also another interesting thing, very high redshift clusters have a very small angular size, as I shown before. XMM has a very large PSF. So is the PSF of XMM-Newton a problem? Study high redshift. The answer is because here, for example, I'm showing the ratio between Chandra and XMM density profile, and you see that there is an excellent agreement. So look at the black solid line, which is the average of different clusters that we use for this test. You see that the black solid line basically lies on the identity line here at 1, above, would say, 7 arc seconds. So we are able to reconstruct the density profile with XMM-Newton down to 7 arc seconds. Okay, now that I explain why we can combine Chandra and XMM-Newton, let's look at the results that we obtained. Okay, first what we have done is analysis of galaxy cluster. And what we have done, characterize the dynamical status of galaxy cluster. So what we do in X-ray is we look at galaxy cluster here, and we try to identify if the galaxy cluster is perfectly round, which means basically that the galaxy cluster is perfectly visualized, or if there are traces of substructures in falling, and so if the merge of the galaxy cluster is disturbed. And for example, we can use a quantity which is called the centroid shift, which basically is the difference between the peak of X-ray emission and the centroid at large scale. So if the cluster is perfectly round, peak and the centroid should be basically the same, and if the cluster is disturbed, they should be very far away. Okay, so what we have done is doing the centroid shift the comparison between measurements. And in particular, yes, what you see here is that 4 of the objects are classified as disturbed because they are greater than 1. So there are some criteria that have been tested to say that if the centroid shift is greater than 1, then the cluster is disturbed. So first of all, we see that the galaxies that we are looking at, they are all disturbed, so they are all undergoing some merging processes. But what I would like also to say here is that the combination of Chandra and XMM is really good for the imaging, because here, for example, you see that you have a diffuse emission here in the XMM-Newton image of this cluster. And this point source, this AGN, just happens to be in front of a substructure. And you can see here the diffuse emission from this substructure. And on the right with Chandra, of course, you see that the flux is much weaker, but also what I would like to say is that here you can clearly identify the presence of a point sources. So you see that the PSF of Chandra also for this kind is crucial to identify the AGNs and to discriminate between diffuse emission of the substructure from the point sources. Okay. Then we perform the 1D analysis. So what we have done is we define the center, for example, the X-ray peak. We define some concentric annuli, and we measure the density in each annuli. So what you see here, functional radius. So what you see here is the density profile measured by XMM in blue and by Chandra in red. And what you can see is that there is a very good agreement between the two density profiles, as I already shown in our previous paper. So since there is a very good agreement between the two, what we have done is we decided fit the two density profile using some very well-known models. And in particular, we use the parametric model from Viklin et al. 2006. And what you see here, which is really interesting, is that you see the density profile in the core, the fit of the density profile in the core is driven by Chandra, while the fit in the outskirts is driven by XMM-Newton. But this is exactly what we want, because we are exploiting the PSF of Chandra in the central part, and we are exploiting the large effective area, so the statistics of XMM, to extend our signal to greater rate. So you see that by combining the two, we are able to extract density profile, I would like to say up to even 200 for all the 5 galaxy clusters. Then what we have done, extracted to extract temperature profile, we do something similar to what we do in the density. So we center the X-ray peak, we define some annuli, concentric annuli, and we extract the spectra. Now, in the X-ray, extract spectra is much harder than density because we need to have much larger statistics. So these annuli are very large, and the extent of these annuli is, as I told you, this is very for this sample because it's very hard. At redshift 1, the signal is very low. But as you can see here, with these black points, we were able to extract the temperature profile for all the 5 galaxy cluster up to R5 for our measurements. Here you see also other shapes. I won't enter in the details, but what I would like to stress is that all these other colored shapes that you are seeing correspond to different techniques that we can use in X-ray. And what you see interesting is that apart from this cluster, which is a very good agreement between the data points and all the techniques that we used. So this means that even at this redshift, the techniques that we are using in the X-ray are really, really robust. Then, since we have density and temperature profile, we can combine the two, and applying the hydrostatic equilibrium assumption, we can measure actually the mass profile, the hydrostatic equilibrium mass profile. And the nice thing here is that points here represent the data points, okay? The data points where we were able to measure the mass where we are able to measure the temperature profile. And the nice thing here is that you see that all the different methods that we can use, they are very robust. They more or less give the same results. But if you take a very disturbed cluster, so one which is undergoing a very violent merge, as we depart from the black points, so as we extract the signal, you see that things go crazy. Basically, what is important here is that if you start to use different techniques to extrapolate at higher radii or in the center, and your cluster is very disturbed, you get completely wrong results. And the important thing here is that you need data points to have an accurate and unbiased measure of your mass. And this is what we try to do in this work for this cluster. Okay, so we were able to individual profile, and what we are interested in now is trying to do evolution. Now, to do evolution, we have to compare the properties of our clusters at shift 1, a local sample. For the moment, a very large SZ selected sample. So what we have done is chose REXCESS. Now, that you can see here in the mass redshift plane with the yellow points is a local sample which has a very large range of masses here. Now, the characteristic of this sample is that it's at redshift lower than .2, so it's easy to do evolution by comparing proper clusters with REXCESS. It is very well selected, and also it is tailored to fully exploit XMM-Newton characteristics. So the analysis of this sample is very well done and it's very detailed, and we have a lot of information available. Beware of the fact that our sample is here, so our mass range is very limited, and REXCESS is very large, so the comparison samples must be done with careful because the mass ranges are different, and also be aware of the fact that REXCESS has been selected in X-ray, and our sample has been selected using SZ. So there could be differences also related to the selection effects. Okay, now the first thing we have is pairing the individual density profile that you see here with colored lines with the REXCESS dispersion. And in particular, you see here in light green the 68% dispersion of all the REXCESS profile considering whole sample, and in dark green considerably the disturbed cluster, so the cluster which are undergoing violent merger. And what you see seems that our profiles are somehow lower than they are in very dark. Now, actually, what the reason for this is that, as I said, our sample here with colored points is characterized by disturbed objects. So the only reason why we are seeing this small offset as respect to the whole REXCESS sample is simply related to the fact that we are looking at objects. So evolution in the density profiles. Now, another thing that we have done is we have looked at the at the evolution of pressure profile and entropy. Now, what you see here is that there is a very good agreement. So here are the cluster of our sample, and the dark and light correspond to the REXCESS. Now, what you see is that there is a very good agreement between the pressure our individual pressure profile and the dispersion of REXCESS, and all the entropy. You see only here one outlier, but in a very good, in a very wide radial range, there is a very good agreement also profiles. Now, one thing that you can notice is the fact that here there seems to be a flattening of the entropy profile. Now, this is actually a very well-known effect in the X-ray community, and this is not actually, but it's simply caused by the fact that when you look at very large radii, you have some very cold cluster in the cluster and may bias your results. So we don't think that this flattening here it's related to an actual evolution. So our suggestion is that there seems to be a very good agreement, so there's not a very clear sign of evolution for pressure and entropy. These results are also confirmed by the analysis performed at McDonald, where they looked not at individual profile, but the data of a lot of galaxies, same shift range of our. Okay. We looked at the end at the total density and the hydrostatic mass profile. So we have done the comparison between our individual profile, rho here is the dark matter, and the hydrostatic equilibrium profiles. here, which is really interesting, is that you see two different behaviors in the inner part and the outer part. So here in the outer part, you see that there is a very good agreement between our profile and the individual REXCESS profile, here shown with these light gray solid lines. While in the inner part here, you see that our profile seems to be shallower, and in particular you see that there are two big outliers here, maybe even three. Now, the real point is that we are working only with 5 galaxy clusters, so of course we cannot do any type of quantitative statement, but at least what we can do is say that there is question for a presence of evolution matter inner profile, or maybe it's just an increase of the of X-ray, but at least we were able to identify some features. Okay, then look at a quantity, which is the sparsity, which is defined basically as the ratio between the mass computed at 500, which is where the density contrast of the cluster is 500 times the mean density of the universe, and the mass measured at R 2500. So basically what we are doing, this sparsity, is measuring the shape of the mass profile at different points. And what you see here is basically confirming what we have found before in the total dark matter profile. So here, these gray and dark green lines represent the histogram of REXCESS. And so you see that the distribution, which is this new proxy for REXCESS, is very, very narrow. But at the same time here with blue, you see the 5 cluster. And what you see is that there are 3 clusters which are and 2 which are completely outliers. So at least we confirm our previous results. And also what I would like to say is that these work together with Corasaniti et al. These are the first works that are actually trying to use the sparsity to characterize galaxy cluster population. And what is nice here is that you see the effectiveness of the sparsity in characterizing galaxy cluster population. Okay, then we look at the baryon fraction. So by Planck as a thing. Here in gray you see the baryon fraction measured by REXCESS, the 68% dispersion, and here in black you see our actual instruments. Here you see only 4 galaxy clusters, because for one galaxy cluster, because for one of the 5 we didn't have the stellar fraction. So what you see here is actually there is a hint of evolution of fraction, and this telling us is that higher redshift cluster should be denser. So at higher redshift the cluster denser, so it was more easy to adjust. This is something that has been predicted by simulation. And for example here, these purple points represent actually the result from the simulation of Lebrun et al. 2015. Okay, then we looked at the evolution at the ratio between the M500 hydrostatic, so the M500 measured using the hydrostatic equilibrium profiles, the M500 measured by... Now, here basically just focus on the right-hand plot, and what you see is a very good agreement, a mass measured using the profile and a mass measured using the proxy. It's nice here, this plot suggesting the fact that the M500 REXCESS, so this is being calibrated on REXCESS, which is a sample where they use hydrostatic, where they measure the hydrostatic masses assuming circumferential evolution. So basically they calibrated this proxy local sample where they used hydrostatic masses from relaxed objects, so objects for which are not undergoing violent merger. And then we are applying this proxy also at a sample redshift 1, which is characterized by disturbed objects. Then we do the comparison between the y-axis and there is still a good so this plot testing the fact that the y-axis proxy can also apply to other other sample, to other extreme sample, and also that there is no clear sign of a departure from a self-similar. Okay, then another done is we compared our masses with lensing. Now, what is interesting here with weak lensing is now what is interesting here is that on the x-axis we plot our masses. On the y-axis we are plotting the weak lensing. What you see here is that first of all, there is formally a good agreement between our masses and weak lensing. But the problem is that there is a systematic seem to be higher than weak lensing. And this is a bit weird because actually what is predicted from other where they see weak lensing masses using optical, what they've found is for example from Weighting the Giants or from CCCP is actually the contrary. For example, with red line, actually X-ray masses should be systematically low. Weak lens, because we assume that there are some biases in the X-ray. So the fact that here we find different is a bit weird. Again, we only have 4 objects, and formally everything is consistent. But this is suggesting that something is going on when you're looking at these kind of extreme samples. Okay, last thing that we have done is we compared our profiles with simulations, and just by chance, in the cosmological simulation that we are producing within the M2C project, we only have galaxy cluster, simulated galaxy cluster, that are shown here with this black solid line. Now, what you see is that basically there is a very good agreement, but the fact that we only have, as observers, we only have 5 objects, and the fact that we have 5 simulated objects, agreement the only coincidental, so this could be only a coincidence that there is this very good agreement, and also what to do is increase the precision of simulation to inner core, so in the inner part of galaxy cluster. Here are my results. So first of all, I've shown the very good synergy between Chandra and XMM. Now, combination of the 2 instruments allowed us to the problem of the cosmology and to get density profile up to 500 and to get individual temperature and mass profile up to R500 at redshift 1. Thing that I would like to stress is even though these observations are challenging, we were able to get measured masses which were robust. Then, by comparing these robust measurements with REXCESS, we were able to show some hint of evolution and also maybe some apparently large matter. But the limited number of objects doesn't allow us to quantify if this is due to evolution or if it's something related to the fact that there is a very different mass range between REXCESS and our sample. One thing that I would like to point is also there are works which use stacking. So they stacked a lot of observation to overcome the cosmological dimming and retrieve some good statistic. But when you're doing stacking, you are losing information on the scatter, so on the individual scatter of the profiles. Stacking is very efficient, but you lose information on the scatter. And then another thing that I would like to point is that small tension between X-ray and weak lensing masses, formally in agreement, but maybe there are some effects that we should look at. And then, just talk about future prospects. What about the future? So first of all, continuing with this M2C, we would like actually to populate high redshift samples. So we would like to include more analysis objects and do the same analysis. And also, I am doing now the analysis of in collaboration with Monique and Gabriel. We are doing the analysis of the BMI, so the redshift between redshift .5 and .7, where we will have 30 objects. So we will be able to quantify a bit more what we are finding. Then, what I would like to say is that REXCESS has an X-ray selected sample. So what about an SZ selected sample? So tuned for the results of the Chandra XVP led by Chris Jones, the XMM, which is something that it's going on and it's led by Steph. Then another interesting thing is that the SZ facilities, new SZ facilities are incoming, and in particular, new facilities which are comparable to the one that we have in the X-ray. So we will be able to increase our ability to do to study the physics of galaxy cluster, and in particular, stay tuned for results from Instituto. Then also from the simulation side, we need to employ large volumes, because for the moment we only found 5 clusters, but of course we would like to have more. And then another thing that we are doing now is the combination with optical. So we are looking at combining ray profiles with optical profiles, and basically it.
Any questions?
Well, thank you very much for this nice talk. And I would like to ask you about, well, you know the tension that there is in the cosmological determination from sigma 8 and omega m between Plancks and when you include the galaxy clusters, no? This is, well, well, I think maybe there is a bias in the scaling relation between SZ and X-rays, which is assumed to be 0.8 for the computing the cosmological parameters from CMB, from Planck, no? So have you compared, in this sense, have you compared your masses, your X-ray masses with the SZ mass computed by Planck or not?
Yes, and actually there is a good agreement, but we didn't do the compare because we basically with only 5 objects we will not be able to tell anything, and anyway we use the YX and we see that there is a good agreement. So now I remember the numbers, but we know that the measurement from the YX and the YZ it was quite good. So
you think that you can find a 1 minus p value around 1 or something like
no,
that?
We didn't look at that,
you don't
because
know.
We don't have really the statistics to do that.
Okay. This is very controversial, you know, no?
Yeah,
this subject is now very controversial because when you use a dynamical analysis of the optical velocity dispersion to compute the optical mass, you find some values in this bias, or when you use weak lensing or X-rays, and each technique produce or several very different biases. So this should be a very nice analysis if you do with this, at least for these 5 clusters.
Yes.
Okay, that's good. And then I would like to enhance that the importance of combining data, not only inside or not only X-ray data, but also optical, weak lensing, SZ, because this is the only way that you can understand what is happening in the clusters. No?
Yes.
This is the only way. No, of course you can trace very well the hot intercluster medium with X-rays, but also you can detect substructures better with optical, or determine the mass with weak lensing, etc., etc. So I think that this is the multi-wavelength analysis of the cluster is the only way that we can analyze the close or nearby cluster and compare with the high redshift cluster. No?
Yes.
Well, thank you very much.
Thanks. So this mass difference you get between the X-rays and the lensing, I find very interesting. It reminds me actually of a study. We did a study in M87 where we compared dynamical masses from the stars, globular clusters, and planetary nebula to the X-rays, and the X-rays were always higher. So I guess people do this. Maybe Rafa does this. I don't know. But do people compare for local clusters dynamical mass estimates, say from galaxies or whatever, to the X-ray mass profiles? And if you do that, do they agree, or do you also see this offset in the sense that the X-rays give you a higher mass as a function of radius?
No, because we did the comparison between, for example, the masses from REXCESS, the YX from REXCESS, and the hydrostatic YX REXCESS and hydrostatic YX in our sample, and we found a very good agreement.
Okay.
So that's the basic basic what I'm showing here, because the YX has been calibrated on REXCESS. So that's the point, that we tested the fact that if you take something which has been calibrated on REXCESS and you apply, you get basically the same thing.
But the REXCESS is not a dynamical mass measurement, is it? What's the mass measurement from REXCESS?
It's hydrostatic equilibrium
So you
masses.
assume
Yes.
hydrostatic equilibrium, right? So if you were to compare it to a different technique,
yes,
which would be, say measure the mass profile using how the
the
galaxies move.
No,
Okay.
I'm not aware of this kind of.
That would be interesting to know whether there's any agreement there, or if you see this offset.
Regarding the comparison with simulations, how did you exactly did the comparison? I mean, did you generate some sort of mock observation, then you apply the same procedure you used on observation, or you just get the profiles from the hot gas simulation?
Okay, we start from dark matter only simulation. We directly get all the very nice profiles directly from the simulations, and then we try to mock a bit what we do in X-ray. So we got the pressure profile from the simulation, but full resolution, and then we apply the hydrostatic equilibrium. So we got something directly from the simulation. We didn't start from a mock observation, but we tried to mock the X-ray techniques that we did.
Someone else want to have something?
Could you show us the plot with the baryon fraction?
Here it is.
Okay. I mean, okay. So, two things, or at least two things. So, the first one is that why you get baryon fractions that are smaller than the cosmic baryon fraction. So, what is the mechanism that is like getting rid of the baryons that you have in the clusters? And again, in order to compute the baryon fraction, you need to know the baryons and the dark matter that you have there. So all these biases that you have been mentioning are going to affect the value, the final value that you end up with. And so those points, right? So is it true that the baryon fraction is smaller than the cosmological one? First, and what is the physical mechanism that get rid of these baryons? So,
okay, so first of all, we got the baryon fraction because we measure the hydrostatic mass, and we get the gas mass profile. I mean, from the density profiles, we can integrate and get the gas mass profile. And so this is how we get the baryon fraction. Then we have the star fraction from Q et al. 2016, and so that's how we get the baryons fraction in total. And from the hydrostatic equilibrium, we get all the mass. So that's how we get all the different fractions. So I didn't plot the gas mass fraction. Okay, and then what we are finding, this is in more or less good agreement with simulation. Okay, where you see the purple points, our black points and the purple points.
So the purple points
are simulation from Lebrun et al. 2014.
Okay, I thought it was the other way wrong.
No, the black points.
You basically get the cosmic baryon fraction.
Yes, exactly. And the reason that, the explanation that we got from simulators is that at higher redshift cluster we're denser. Okay, simply because the density was. And then it was more difficult to eject the gas. So that's why you retain more baryons. At least that's what.
So that was part of my question. So eject the gas where? To the intergalactic medium? And what
the
is
other parts?
to the outer parts?
Yes, to the outskirts, if you want.
And what is the mechanism that
Uh,
ejects this gas?
I guess it's related to the AGN in the center, I guess. But I'm not
So the
very
AGN is able to...
I don't know, maybe with the bubbles, they're rising up. But I don't know, I mean, I'm not really... I don't know exact mechanisms.
No, it's not really heating up the gas, because, I mean, I have this naive impression that clusters are always accreting everything. So nothing escapes. But somehow you're telling us that part of the gas actually escaped out of the... So it's not just accreting,
I think
but part of the baryons, so of this gas, makes it back to the intergalactic medium. And I wonder how this might happen.
I think this is a combination of, first of all, you have, for example, interaction between some clumps. For example, you may have some subclumps passing by, and if the dark matter potential is not good enough, you may have some gas which is stripped away, or you have the AGN inside which is inflating, and you have some bubbles which are...
This implies some kind of separation between baryons and the dark matter. So
Yes.
all this passing by thing should affect both to the baryons and the...
Yes, that's true. But I don't know the specific things that are happening. But I think that if you have a combination, for example, I can think of, as I said, you have something passing by and you have some gas stripping. So you have maybe the two dark matter. Maybe you have the two dark matter potential that start to hobble a bit because of the gravitational interaction. But then you have the gas which is stripped away. And you have also bubbles
I mean,
rising
if
up from
anything,
the
it should be
AGN.
the other way around. So it's the gas, it's
No.
the baryons that
Yes.
should be kind of trapped
Yes.
because you have these extra hydro forces. And if something is going to pass by, it's the dark matter. So somehow, I don't understand how this happened, but
Yes, but
it happened.
The last two questions, because we have to close.
Returning to the weak lensing bias, and did you not calculate did you not make an analysis of weak lensing of these 5 clusters? Because I think this blue and red line are not made with this.
no. These blue and red lines are what is expected for the 1 minus b, so for the expected bias from other works, from Weighting the Giants and from CCCP.
But it is possible that you are overestimating the mass because these clusters are disturbed.
Yes, it could be. But the problem is that what is predicted is generally the other way around.
Okay.
Because you are somehow underestimating the... You have the non-thermal pressure support. And so you have this bias. But it's predicted to be the other way around. And one thing that we did to somehow try to match the weak lensing masses with our X-ray masses is that we computed all the X-ray masses that you see here, we computed them at the area 5 the weak lensing. So trying to minimize all the possible systematics.
Okay. And to calculate.
Yes, exactly. Yes. At least we tried to reproduce what we could from the weak lensing. And also what I would like to stress is the fact that we are also using the infrared YX. And the YX proxy should be not so sensitive to the fact that the cluster is disturbed.
Yes, but the YX proxy is the scaling relation is characterized with X-ray
Yes,
data.
yes,
So
that's for sure. Yes.
it's obvious that they are in agreement. Okay. And you calculate the mass, the pressure, the mass profile with the Arno 2010 profile.
1000. Sorry, can you?
You
repeat again?
calculate the mass profile using the Arnaud profile.
Yes.
Thank you.
Last question. Didn't you have a question? No? Okay, I think if you have got any more doubt, we can discuss in the library where we have got the scientific library. And then we can thanks again, Iacopo.